Good morning, all of you, and welcome to 4Vision Instruments webinar series. Today, our webinar will be on Bruker's exclusive PeakForce Tapping for 10 years and counting. Our presenter is Mr. Yogesh Jairam. He is a key accounts manager in Bruker Nano Surfaces Division, Chennai. Uh, I need to give brief introduction about Dr. Yogesh Jairam. Dr. Yogesh Jairam responsible for application development and technical support of surface metrology and tribology instruments. His academic background was in solid state physics and material science. He obtained his PhD in KU Leuven, Belgium, working on linear and non-linear optical effects in metal nanostructures. Prior to joining Bruker, Dr. Yogesh was a postdoctoral researcher in University of Toronto. He has published in over 15 peer-reviewed international journal papers. He also presented in many international conferences. I wish all I wish everyone be safe and healthy in this pandemic situation. I request all audiences please be mute yourself during this webinar. And if you have during this webinar, if you have any questions or queries, on right side you will find question and answer section and type your questions. We will allow after this webinar, after the presentation, we will allow 30-minute duration for question and answer section. So I request Dr. Yogesh Jairam to take over the presentation.
All right. Thank you, Sarvi, for the introduction. So let me share my slides. Okay. I hope everybody can see it.
Yeah.
All right. Good then. Okay. So today, like Sarvadi was mentioning, I'm going to talk about PeakForce Tapping. It's been 10 years, slightly more than 10 years since the launch of the technology by Bruker. And this is maybe like a brief overview of how this technique has evolved and what are the things that it can do for researchers in different disciplines. Yeah. So just going to be a brief overview on these different techniques. So PeakForce tapping is actually one of the most significant breakthrough. So, you know, in AFM, everything relies on the basic imaging mode, like used to be contact or tapping mode. Um, Tapping mode was also launched by our company. Then now, after several years, the PeakForce tapping was launched, right? So there are many significant benefits from it. So you can get very high resolution images on any kind of samples, right? Like soft biomolecules to very hard materials. And not only that, it can add other quantitative results like mechanical, chemical or electrical data. And we have also made it easy for everyone to use it, right? So many of you may be experts in biology or material science, but not themselves expert on instrumentation, right? So we want you to be able to use the technique quite easily, so to study your research problems. And this can be done now without having to bother with a lot of these parameter settings, etc. So that's really remarkable. On the right side, you see a little bit of a timeline from the time when the PeakForce tapping was launched and the different developments there. So in 2010, the PeakForce technique was combined with electrical techniques to get the PeakForce Tuna. Then you can get the PeakForce KPFM, which improves the resolution and sensitivity of the KPFM by at least a factor of 10 to 100. And then we have other patterns for mechanical properties for life science, high accuracy mechanical packages, and also including things like microwave impedance and CCM. So you can see over the 10 years, there has been constant developments and additions to make the PeakForce tapping reach more and more research audiences, right? And so that's the key concept. And it has been very productive for many of our customers too. So you can see from 2009 when it was launched, now we have over, yeah, so 4,000 articles in 2018. And you can see across the different areas, right? So just from imaging or mechanical properties or electrical measurements. And some of these testimonials from our customers from across the world. You can see talking about their experience with biomaterials like live cells, polymer materials, and electronic materials, electrochemical materials, right? So across various disciplines, we can see there is real impact. So if you take this technique alone, there has been more than one article published for every day, continuously for 10 years, right? So that proves the power of this technique is not just a technique in isolation, but that can give results. In this case, the results for academic customers, right? Okay, so before we understand the breakthrough in PeakForce tapping, it's also good to understand what are the techniques that was there before, right? So the one of the common techniques that we had was contact mode imaging. So where you're basically dragging the tip across the sample, right? It's a very useful technique. It is very simple to set up and run, but it damages soft sample. It can have unstable interaction force, and you also have tip damage sometimes, right? Uh, Nevertheless, this technique has been the underpinning for many advanced modes like conductive AFM, capacitance measurement, spreading resistance, or thermal measurements, or lateral force measurements, right? So all these measurements that you are familiar with are based on contact mode. So without contact mode, none of this is possible. So this is still a powerful technique. And in the contact mode, you can also get this what's called the force volume measurements or force curves. So you are coming, engaging, and retracting, and you can get this multiple data. And it can give you mechanical data as well, right? So very powerful that way. The only drawback is this very slow for mechanical data collection. So it can take even 5 hours for even a measly 128 by 128 pixel image, right? So that's the contact mode. And the key way that contact mode is defined is basically based on the feedback loop, right? So you have the tip bending, and you are monitoring how much is the tip bending, or is sometimes called the cantilever deflection. So people who have used AFM might know when they do the contact mode imaging, they will do something called the deflection set point. So that's basically defining how much of the cantilever deflection or the tip bend or the cantilever bending that I am wanting to maintain across my entire scan. And this is the feedback. That's the loop that maintains that constant level of deflection, right? So then Bruker or the instruments in their previous avatar as a digital instruments patented the tapping mode, and it was launched. Now it's known by many names. People call it tapping mode, intermittent contact mode, and non-contact mode, etc. But they are all basically the same technique. So you have a cantilever, and you apply a AC signal to this piezo. So you oscillate the cantilever at a fixed frequency, which is very close to the resonance frequency typically. And you're looking at how this amplitude is going to change, right? So when I'm oscillating, I am oscillating at a fixed amplitude, depends upon whether I'm close to the sample or further away from the sample. This amplitude of the oscillation will change, and this is what I am feedbacking on. It's a good technique, so you can get a certain electrical data like EFM, MFM, KPFM. You also get phase imaging, which contains some mechanical data, like but it doesn't give you very quantitative details. And one of the major drawbacks of the tapping mode is that it's to operate it in ambient or air is pretty relatively okay. But once you have the need to operate under liquid, for example, biological samples or whatever, then it becomes very impossible, because you want to find the resonance of your cantilever. It's very difficult to find. So if you tune your cantilever typically under liquid, this is what you're going to get. And you basically have to guess which is my resonance frequency and how do I set up this amplitude points, right? So it's a hit or miss here. And this is one of the major drawbacks. And of course, you don't get a lot of rich electrical data like conductive AFM. You don't get a lot of mechanical data. I mean, in fact, you get very, very minimal those kind of data that people are now trying at. Imaging is okay, but yeah, these other advanced modes is still a little lacking. Yeah, but we did mention that the phase contrast give you some mechanical data, but it's very unreliable. So you can say if I change my amplitude of my oscillation, go from a lighter tapping to harder tapping, you can see my phase contrast inverse, right? So it's very difficult to say which is the harder material or which is even the softer material. So it depends, right? Depends on what kind of tapping you are doing. And this can be a very so it can give you some contrast, but it doesn't tell you much more than that. So here comes the PeakForce tapping technique. So PeakForce tapping takes the advantages of contact mode and takes the advantages of tapping mode, right? The advantage of tapping mode is that there is no lateral force, right? So that means very low sample damage. Uh, the advantages of contact mode is like, well, you can get the force curves at every pixel, you can get conductivity data, etc., etc. And that's what we can do. So in this case, um, the key difference is this. So in contact mode, your feedback is based on cantilever deflection. In tapping mode, your feedback is on amplitude change. In this case, you are actually measuring the force between the tip and the sample at every pixel, right? So that's why the name, the PeakForce tapping mode. So you get every pixel, you're going to get a force curve. Uh, so the great breakthrough basically happened in ability to get this force curve at every pixel or every pixel interactions at very high frequencies, maybe up to 8,000 times a second. So that means there's a lot of clever understanding of the science, what are the different dynamics that happen there, and how do I remove that dynamics from the background signal, etc. And then you get this also avoid kind of like force overshoots and things like this, so you can get really well controlled and well defined force curve at every pixel and at up to 8,000 times a second, right? And because you get this, you can basically get all the mechanical properties like modulus, deformation, dissipation, adhesion between the tip and the sample at the pixel. And this is off resonance technique. So that means you are not operating at the resonance frequency of your cantilever. That means you can also use this technique for other advanced measurements like we will see before. And you can also do great automation, right? So let me see why this doesn't play. Okay. So here, well, anyway, so it's multiple cartoons here. So you can see it's a DNA image under liquid. This is using the PeakForce tapping mode. So each DNA strand is about 10 to 15 nanometers or so. And while it is doing, you can see the force curve is constantly being accumulated at every pixel. So the force curve changes depending upon whether I'm on mica or I'm on DNA material. And you also do the full optimization, right? So your set point, gain, everything is automated. And you have no need for tuning because we are not reliant on the resonance of the cantilever anymore. So we can do it at any point, any frequency we choose to, right? So that means if you are, let's say, a biological user and you want to image DNA, you don't have to worry about all the instrumentation part. You prepare your sample, put it under the AFM, and press play, right? The system fully optimizes it. You get the very high resolution DNA without the need to do cantilever tuning, without bothering about set points and gain settings, etc. and you can even get mechanical data at the same time, right? So it's ultimate in ease of use, right? So basically you can automate in all kinds of environment and all kinds of samples. So here are some very, very challenging samples for imaging, like polymer brush using scan assist. So the whole scan is about 750 nanometers by 750 nanometers. And you can also see some very high resolution DNA origami, right? So robust self-optimizations under all kinds of operating conditions, liquid, ambient, soft material, hard material, etc. It can track any surface. You don't need to know what kind of surface is there, what kind of pattern will be there, etc. Right? Anything can be done. There is no requirement of cantilever tuning. This is a real big thing, right? Especially when you're doing very soft materials or under liquid imaging conditions. Consistently high quality data uh, without, doesn't matter what's the user level is. So it's fully automated. Some translation, how does it translate into real life? So here is an example. So this is it's a really a large hole, maybe about 8 microns or so. On across this hole, the researchers have suspended a graphene film, okay, a monolayer graphene. And this graphene bows across this hole because there is no support below it, right? The substrate is all here, and there's no substrate. Now, no substrate here, so there will be a bowing of the graphene. And if you have to image these kind of samples in tapping mode, it's basically like hitting a drum, right? Getting all kinds of oscillation is so difficult to image it. Basically, don't succeed at all. And here you can see with the PeakForce tapping, very nice. So this is a cross section of this sample. You can see this is the substrate, and there is the bowing of the graphene film, and then you have the substrate again. So very nice image you can get. And this allowed this user in this case to study the mechanical properties of the graphene without being affected by the substrate, right? So they can do the modulus fitting, and then they found the modulus of is about 350 Newton per meter experimentally, right? So this is one of the interesting data. And another thing, of course, you also do not sacrifice any resolution. So you can see here, this is atomic resolution of calcite. The scan is about 16 by 16 nanometers. It's very high resolution. You can basically see atoms protruding atoms here, and you can also see some defects in the lattice, right? So, that's the high resolution we are talking about. And this is now accessible to pretty much to every user of the AFM without worrying about anything. And again, here is a submolecular resolution. And this is actually a mechanical property data. This is not topography. What you're seeing is the addition, how the addition is changing across the sample of IPMMA sample, right? Across your, that's what you're mapping there. And this is the graphene that we previously talked about. And here are some examples here of the high resolution and at the simultaneously measuring the mechanical properties, right? So this is the topography of the PDA crystal. You can see already some defects in the crystallization. Well, you have some problem there, lattice defects. And you can also measure the stiffness or the in atomic resolution and addition between the tip and the sample in atomic resolution, right? And yeah, so you can see that this is the same PDA crystal, and you can overlay with the models that's previously known. Now you can clearly see all these aromatic rings and the lattice spacing, etc. Different examples with the PDA crystal, mica, calcite, DNA. You can even see in this case the minor groove, the major groove, and you can clearly measure the pitch and everything. Yeah, so very high resolution at a push of the button, right? Yeah, so some more examples from the world of life science. So here is a really great data that basically shows these kind of very fine projections. These are called the microvillis on a living cell. So if you fix a cell, you will not see them. They will usually get destroyed. These are very delicate ones. So you need the cells to be alive. That means you are measuring under liquid condition. And even the force that is used in the tapping mode is too high for these kind of imaging, right? Usually you will destroy them, even if you use tapping mode. So to do that with PeakForce tapping is the only possibility here. So you can now control the force levels in piconewtons, right? 50 piconewtons pretty easy, maybe even single digit piconewtons. And you can do the measurements on any kinds of sample there. Yeah. So now I want to talk about nanomechanics through this. So you get basically with the PeakForce tapping a fully calibrated out of the box. You get nanomechanical properties not across just sample, but every pixel is a nanomechanical data, right? Atomic resolution nanomechanical data that we seen before. So you can see here, when you do a tapping mode, you get this and phase. You do not know what this means. But here you can see the height, the addition, the modulus, and other parameters, whatever you desire, dissipation, etc. This is all done in single pass, right? So you do one scan, you get 8 different channels of mechanical data at the same time. You can also do imaging. So here, if you see this image, okay, so I can see there are 3 different phases, the really light blue, slightly darker one, and the black one, but you do not know which is what. So then when you do the modulus mapping, you can clearly see the C is the softest material at a few megapascals, and the A and B are the much harder at a few gigapascals, right? And so this ability to pinpoint which material is where based on the mechanical property really is a powerful, especially these days, most materials are complex chemistry and complex composition, right, in material science. So it's very a powerful technique there. Uh, so here is an example of the same. So here is your topography. So there is PP and EPDM, 2 polymers. You can see at the interface, you have basically no idea which is what. Then once you look in the modulus, it's very clear, right? This is the very hard material. And then this is much softer, and you can even quantify them. So it's 1.7 gigapascals, this 15 megapascals. It's a huge dynamic change there. And you can also look at the adhesion channel, and here the contrast is inverse, whereas the EPDM, which is a softer material, has a much stronger adhesion to your cantilever than the PP, right? Okay, so then you can look at different materials. So here is one of this kind of like a packaging material with silver nanoparticle, which is antimicrobial. And you can see in this high channel, you have no idea where these silver nanoparticles are. But if you do the adhesion mapping, you can very clearly see where the silver nanoparticles are. Even if you do the mechanical one, you can clearly see that. And you can also overlay these kind of things on with the temperature changes, right? So here you basically have a melting of SPP and PO, and we are recording images as the temperature is increasing, and you can see the material soften. That's why it becomes a little darker, right? So the harder material soften, and you can see these kind of fibril structures. These don't soften that much, whereas the bulk of the matrix is softening much more rapidly as the temperature is changing. These are very high resolution, so it's about 500 nanometer scale bar, and you can clearly see this. So in the old days, you have no idea what's happening when you heat. Now you can actually point which polymer is softening and where it is going, how the soften process is progressing, etc. Right? So that's the power now. On top of this very high resolution topography, very high resolution mechanical data, you can now correlate it also with electrical data at the same time, right? So here we are going to talk about 2 specific electrical data. That's the PeakForce Tuna, which is also the conductivity measurements, and also the surface potential, which is like KPFM data, right? So that's what we will look at now. KPFM in a traditional sense is done based on the tapping mode, right? So if you're using a tapping mode, anybody who've done it know you will use generally a stiffer cantilever so that you can see the resonance of the cantilever clearly, right? So that means your K is going to be very large. And the quality factor of these cantilevers are generally not too big. So your sensitivity is quite limited by the underlying technique. And because of that, what kind of probes you can choose. But because the PeakForce tapping doesn't really need to be at the resonance frequency of the cantilever, we can use a very, very low K cantilever or a very soft cantilever, at least easily 10 times softer than the tapping mode, right? And you can use at the same time a very large Q. So you can see if you have a 10x factor here, 10x factor here, you can right off the bat improve your sensitivity by two orders of magnitude, right? And we also improve the accuracy by using the frequency modulation instead of the amplitude modulation. So here, you can see here, if you have the KPFM with the frequency modulation, you are basically looking at two different material, which is SN and PB. And we know theoretically the difference between them is about 240, 250 millivolts, the work function difference. Whereas if you use the AM technique, you only measure as 100 millivolts, which is not correct, right? Even though you see the contrast, the quantitative data is not accurate. So that's why we use the frequency modulation implementation to do that. And here is on the sensitivity part. So it's a single strand carbon nanotube, and it's only 2 nanometers at the very, very edge, right? And you can see here the KPFM data even able to clearly identify such a small material in a work function data. You can see in the topography, and you can clearly differentiate it from the substrate, right? So again, now we can just to show the strength of the you can see here we have the height, the deformation, adhesion, and the KPFM data together of the very complex polymer brush kind of brush polymer on mica. So this just shows strength. So like, for example, if you have some contamination, yeah, you might not be sometimes very difficult to catch it with the potential data alone, but now you have multi dimensional data on your sample, you can clearly identify what is causing what kind of signal, right? So here is another example. So you have the this is like a rubber material with the different compositions. So PP, EPDM, and some carbon black there. So this is the topography. You have no idea what's there. Then you can see in the modulus data where these items are. And once you look at, let's say, the work function or the current data, you can identify where the carbon black is, right? The carbon black is the most conducting material. The polymers aren't. And you can clearly identify that they are much, much smaller. So even in the modulus data is not so clear, but you can clearly identify them once you do the electrical measurements. So you are able to do all this, through PeakForce tapping. So traditional conductive AFM, unlike KPFM, is based on contact mode technique, right? So contact mode technique, or that means you have all the problems that come with contact mode. You have tip damage if your sample is hard. Remember, if you're doing conductive AFM, you're using a metal tip, metal coated tip, and metal is generally much softer material than like silicon nitride or something, right? So if you're using this kind of metal tip to image semiconductor material, you have tip damage. Or if your sample is very soft, like your polymer material, something softer, you might have sample damage. And because of these two, you have a problem of reproducibility, and you also have sometimes reduced resolution, etc., and some artifacts created by that, right? So basically, pretty much all samples have some problem or the other when doing conductive AFM. And why can't we do tapping mode conductive AFM? So tapping mode conductive AFM, people are unable to achieve that because you are oscillating your cantilever at close to the resonance frequency, right? And that means you do not have control on the contact time. It's very, very short. And you might need a very high bandwidth amplifier with very high sensitivity, which is not really feasible at the moment. Because we use PeakForce tapping and because we are very far away from the resonance of the cantilever, we are able to uh, implement a very high bandwidth current amplifier with very high sensitivity, picoamp or femtamp sensitivities, right? And we can use that to uh, achieve conductive AFM, but basically in tapping mode. So because this is like tapping, you are doing oscillation, there is no lateral force, there is very limited tip sample forces, and you also have very good control on contact times, and you can optimize everything, and you can get no artifacts because you directly control the force. You can optimize it, self-optimize it, like the ones we show through the scan assist, and you can correlate it with the QNM data, right? So here are some challenging samples you can see. So this is basically like a nanotube that's just lying on a substrate. It's not fixed or anything. This is the topography image. And when you do the current image, you can see a very nice image of the current that's being only through the nanotube and zero current on the substrates, right? And if you're doing contact mode imaging, you can easily dislodge these fibers which are just resting there. You just scan with contact mode, you will just drag them across, and you might not get, and you can even see that the current is not uniform across across the nanotube, right? Another example in this phase, so it's just like a forest of nanotubes. So all these nanotubes you see here are standing facing you, so they are like pillars, right? On top, you see sometimes you have this metal particles like nickel or whatever that's used during the growing process. This is the topography. So if you have to image these kind of very delicate sample with contact mode, is already quite impossible, right? And if you have to do conductive measurements, you can forget it in using the traditional conductive AFM. But here you can see the conductivity data. You can clearly see not every tube has the metal particle on top. Only some of them still have, and that's why you can measure the current there. And the ones that doesn't reveal any conductivity, right? So where there is not capped, you don't see any conductivity data. So these kind of things are really the power. And again, like we mentioned, you can correlate it with the mechanical data. So here you have the topography, mechanical addition, and the current. So this is a lithium battery cathode material, L33, and which is active one, and then there is glue and fillers that you can clearly see, right? So even let's say if you have some metal contaminant or something, you might not catch them just with a current map, right? You're still also conducting. But since now we have the addition and the Young's modulus, you can very clearly identify which is which and what's causing the behavior that you see in your sample. And because again, like we are doing the PeakForce tapping and we are oscillating, and we can even do electrical measurements under liquid or electrolyte conditions, right? So you can measure, for example, current or electrochemical currents, EC currents, or contact currents under liquid environments, right? So you can see here, this is just a example of that. So we have a very special probe called SCCM probe, where the entire tip is not covered with metal. Only the apex has metal there. So only what you detect is at the apex of it. You basically have some kind of a lattice pattern here, and that's what you measure. You can see how it changes, right? Measure the current changes across your sample. Has a lot of applications, especially, for example, if you're doing photocatalysis or you are doing, let's say, for example, battery research, you want to know the electrical properties of your material. not in ambient, but will be what will be in the working environment, which will be typically under an electrolyte or something, right? And if you do it in air, it's not really transferable. And this is one of the latest techniques that's been launched by Bruker, something around 2016, 2017. And this is again the same concept, but here what you're looking at is in electrochemical currents as well. So you have the topography, you have the current, and you have the electrochemical currents, right? So you can really clearly see these kind of data, right? So just to summarize, I mean, different things that we talk about here today, and different area of research or applications where it's applicable or what you can think may be useful. So if you're doing imaging, right, under scan assist, no matter which area you're working on, it's going to help you image high resolution, image quickly, and without a lot of fuss, right? No matter where you're working on. And if you're looking at mechanical data like QNM, a lot of applications in 2D materials, energy research, and bioimaging, live cell imaging, etc. Right? So similarly for electrical measurements, yeah, 2D materials, energy research, right? And also maybe some limited applications in cell imaging, electrochemical data like SCCM data with AFM tip, applications for, let's say, energy research, like photocatalysis, batteries, etc. Right? And this PeakForce technique is a really powerful technique. You can actually even invent your own with it, right? So if you want to do PFM, instead of doing a contact mode PFM, you can now do PeakForce PFM. So you can use the same cantilever for a little longer. You can correlate with mechanical data, etc. Similarly, you can do contact resonance if you're doing that, or if you want to even do a capacitance or spreading resistance, and you don't want to do it in contact mode for various reasons. Like I mentioned, typically two big ones. I want to use my tip longer. I want to also protect my samples. So then you can even do these kind of techniques there, right? There are many applications that's constantly evolving, developed by us, sometimes also by our customers. They develop their own modes to solve their own problems, and it's all possible because the fundamental technique has been revolutionary and basically changed one of the key underpinnings of the AFM imaging, right? So that's it from my side. If you have any questions, we can take now. Yeah. Let me see how do I see questions.
Hi Yogesh, thank you for your valuable presentation. So I request audiences, you will have questions, please share your questions on the right side of your screen in question and answer session. We will have half an hour time, so please utilize half an hour time. If you have any questions, please share in the right side screen of your panel.
All right, then. So if you want to write to us your questions, if it's a little bit longer, you can always send us an email. I think then we shall close the session for today, right? So thanks everyone for joining us today.
Thanks, Yogesh.
Yeah, thank you.
Thank you.